So I'll talk about classification of strategic agents who can both game and improve. This is a joint work with Saba Ahmadi, Avram Blum, and Kezia Nejida, who are all from TTIC, and Kezia is also here at the conference. So our paper is on the general topic of classifying the strategic agents. These agents will aim to modify how they appear in order to be classified positive. This could be for getting a loan, for getting college admissions, etc. To appear more qualified, the agents may take different types of actions. We consider gaming actions and improvement actions. Let me explain by an example. Consider as a bank, we want to offer loans to the applicants. We need to decide who is loan worthy, meaning that they would return the loan if they're given one, and who is not. The agents strategically want to show that they are loan worthy, and they may take various actions. For example, they could optimize how they spend money on their different accounts. This does not really make them more loan worthy. It does not really affect how qualified they are. We call this a gaming action. On the other hand, they could take actions that really improve their loan worthiness. For example, they may take a money management class. We call this an improvement action. Recently, there's been a significant interest in the models that have both gaming and true improvement. And here's a non-comprehensive list of really nice papers that study such models. In contrast to most of the papers I showed you, the goal that we consider is to maximize the number of true positives, the positives that we correctly classify as positive. So in our example, it's the loans given out to qualified applicants, subject to few false positives, the loans given out to unqualified applicants. This is something we imagine the bank wants to do. It wants to give as many loans as possible to the qualified applicants because that's how it makes money. And it doesn't want to give many loans to unqualified applicants. What's interesting about this model is that even a perfect classifier may be suboptimal if it does not incentivize improvement. So for example, let's say everybody is unqualified. It's easy to classify them correctly, just not give them a loan. But if instead we could do something to incentivize them to improve, for example, by putting some weight and taking that money management class, they could actually become qualified and we could give them good loans. So it's an interesting setting because classifying the agents correctly may not be the best thing to do. And you could have more true positives by incentivizing them to improve. We're going to consider two versions of this problem. The first one is a linear model, and the second one we call a general discrete model. So next I'm going to explain these models in detail and give the results we have for each. Okay, so the first model we consider is a linear model, and we have points in R. We think of some directions as improvement directions and some as gaming. And the true decision boundary is a linear separator. For example, this is a two-dimensional picture where improvement is to the right and gaming is upwards, and F star is the true linear separator, true decision boundary. In this model, the agents may take a combination of gaming and improvement actions. Let's see on the picture what happens in this case, and when does the agent become truly qualified. So let's say X1 is initially moved here, and then imagine it's going to move to here. Its perceived location, what we observe. For this movement, it did some amount of improvement and some gaming. The improvement takes it to its new true position. So although we observe the agent here, it's truly sitting here. Since the amount of improvement was enough to get it beyond the true decision boundary, the agent becomes qualified. So an agent becomes qualified if by improvement, it goes beyond the true decision boundary. The agents are utility maximizers. They have a fixed value for being classified positive, and they pay a one cost to increase coordinate values while decreasing its free. So for free, they can look worse than what they really are. To maximize their utility, they are only going to move if the value for being positive is more than the cost that they need to pay. And they always take the cheapest path possible. Finally, the algorithm's classifier may or may not be a linear separator. So although the true decision boundary is linear, the classifier could be anything at once. Let's see an example of this. Let's say the improvement cost is twice as much as gaming. We have 3 data points, x1, x2, and x3. And x1 and x2 are negative while x3 is positive. If we use F star as the classifier for these strategic agents, the outcome is not going to be very good. Let's see why. So since let's say that the value for getting the loan is high enough that x1 and x2 want to get beyond the classifier, want to go to the other side. Since the cost of moving up is much lower, they're both going to move up. Since they were negative and they just gained, they become false positives. So using F star leads to 2 false positives. There's a remedy to fix this issue. We could shift F star parallel to itself and use G as the classifier. Based on the value and the cost, we could shift far enough such that x1 and x2 can no longer afford to move beyond the new classifier, but x3 can. So G would classify everyone correctly, classify x1 and x2 as negative, and classify x3 as positive. But it only has one true positive, and this is still suboptimal. Instead, we could use this nonlinear shape here and classify everyone that is observed in this region as positive. Let's see what happens in this case. Okay, starting with x2. x2 has the choice to move to the right, improve, or move upwards, gain. Since the distance of moving up is more than twice more, it rationally decides to move to the right. So it improves and becomes truly qualified. Now let's look at x1. x1 is doing a combination of improvement and gaming. And as we discussed before, since the improvement is getting it beyond the true decision boundary, it's going to be a true positive. x3 also needs to do some improvement to land here and be classified as positive. So now we have 3 true positives. So this classifier would allow the bank to give 3 good loans. It classifies everyone correctly and classifies them as positive, which is much better than just classify them correctly. So this is the kind of the problem that we deal with in this model. Any questions before I move on? Yes.
I guess if there's a ground truth, is the ground truth then only determined by the solution axis?
The ground truth is determined by F star, but if people are not strategic. So if somebody is initially to the left of F star, they are unqualified. If someone is to the right, they are qualified. But then after people move, it's hard to tell. They may be on the right of F star, but maybe they got there only by gaming.
Yeah, I don't understand why when crossing F star would mean that you become positive. Is it kind of like not possible to read off this picture? Like, so I see that you said like I don't come to the right to become positive, but you could also.
Right, exactly. Yes. So what are some of the results we have in this model? There is actually more unknown than known, but here are some of the results we can show. In the special case of 2 dimensions, like the picture we saw on the last slide, there's an efficient algorithm to maximize true positives subject to no false positives. But in general D dimension, this problem is NP-hard. In fact, it's even NP-hard to determine if we can incentivize everyone to become positive. However, we can efficiently find a linear classifier that does this. Efficiently find a linear classifier that incentivizes everyone to become positive in general D if there exists one. And for this result, we use linear programming. Now I move to our second model, which is in some sense more general and in some sense less. We call it a general discrete model. Here we imagine that there's a finite set of potential qualification criteria, and we need to decide which ones of them to take as positive and which ones to take as negative. In other words, what the classifier can do is to pick any subset and label them as positive and label the rest as negative. We view this model as a bipartite graph problem. On the left, we have the agents, and on the right, we have these potential criteria. And the true qualification functions for the agents could be anything at all. Each agent has some cost to satisfy each criteria. So agent I has to pay agent I for each agent I, and each criterion J moving to J has some cost Cij. This movement may involve a combination of gaming and improvement, which may or may not make the agent truly qualified. So we color the edge blue if it truly makes the agent qualified, and color the edge red otherwise. So for example, in this picture, agents 2 may be already qualified. It doesn't matter what they do. But agents 1 and 3 are not initially qualified. They may or may not become qualified depending on where they move to. And what we need to decide is to pick a subset on the right-hand side. So after we pick the subset and label it as positive, then each agent is going to move to its cheapest neighbor in the subset. So they're going to take the cheapest path to become to be labeled positive, or they may do nothing if they don't have any neighbors in the subset. And our goal is to pick a subset that maximizes the number of blue edges taken, subject to a few red edges taken. So the blue edges taken correspond to agents that we give out loans to who are really qualified. And the red edges correspond to people that we give out loans to who are not qualified. So this is a pretty general model, but it kind of requires that potential set of criteria to start with. So our main result in this setting is that we can efficiently solve for a solution that maximizes the blue edges taken, subject to no red edges taken, maximizes true positives, subject to no false positives. And what is interesting about this solution is that it is pointwise optimal, meaning that if we did not give somebody a loan, there was no way to give them a loan without also giving a loan to someone who wasn't qualified. It is also minimum cost, meaning that each single agent is paying the minimum cost among all the solutions that had 0 false positives. So the agents are in total doing the least amount of effort. On the other hand, we show that maximizing blue subject to at most k red is empty hard. So this is maximizing true positives subject to at most k false positives. Okay. Right. So these are some of the results we have for the general discrete model. Another thing we can ask is, what about learning from data? So we assumed so far that we had all the information about the graph. We knew all the agents, all their edges, their costs. What if, and we took this as the input and found the optimal solution. Now, what if we don't have the graph up front? Like standard batch learning settings, we're going to assume that there's a distribution D over the agents. But what does that really mean? So the agents were these nodes on the left, and each node is basically a vector of costs in colors. So the probability distribution is over these vectors of cost color pairs. We're going to consider 2 learning models. The first one is a full information where we see all the out edges of the samples. So we're going to get a group of people, we're going to ask them a lot of questions, and we're going to build a graph for the samples. We also study a natural partial information model where we do not see the out edges of the sample. So here, what we can do is to pick a subset of the nodes on the right-hand side and see what the agent does. For example, we tell them, we're going to give you a loan if you satisfy condition 1 or 3, but not 2 and 4. And then an agent comes along. We see which node they move to. For example, we can check if they satisfied condition 1 or not. And we can also find the color of the edge taken. So the color of the edge is going to be red if we gave them a loan and they did not pay it back. So we're going to do this in rounds. In each round, we're going to pick a subset on the right-hand side and see where the agent moves to and whether they became truly qualified or not. This is very much like online learning, except that here we assume that there's a distribution over the samples. And our goal here is to find a subset with a large probability mass of true positives, say with an epsilon of the optimum, and at most epsilon probability mass of false positives, where the optimum here, our notion of optimum here, what we're comparing to, is the best we can hope for subject to 0 false positives. So this is kind of a bi-criterion objective. We want to be nearly as good in terms of true positives with respect to the optimal with 0 false positives and have epsilon false positive rate. And we show that we can achieve this goal for both the full information and partial information models. To summarize, we studied the problem of classifying strategic agents who can both game and improve. And our goal was to maximize the number of true positives subject to few false positives. We studied different settings, a linear model and a general discrete model, and we gave algorithmic, hardness, and learning results. Some of the problems that remain open by our work. The first one is related to our algorithmic and hardness results. So in some of the cases, we were able to efficiently solve for the optimal solution. And in some other cases, we showed that it was NP-hard. It would be interesting to explore the possibility of approximately optimal algorithms. Maybe those will be tractable. Our second open problem is related to our learning results. We compared the performance of our solutions to the optimum that had 0 false positive rates, the optimum that did not give any bad loans. The case where we want to compete with the optimum with a few bad loans is open. This is all. Thank you so much for listening.